Summarising categorical data has to be very different to summarising numerical quantitative data. So you can't use the same sort of averages and numerical summaries that you can use for quantitative data. So you can only summarise them in terms of tabulation and using graphical methods. So as I said, averages don't apply. So you have to summarise them as absolute numbers, percentages. You could summarise them as ratios, and you can summarise them as two specific terms for 2x2 tables of data, which will come to later, which are called odds ratios and relative risks. So here's an example of a set of categorical data with two categorical variables. This is an example of a two-way table, or contingency table, or cross table. They have multiple names for it. In this particular case, what you're looking at is two particular variables. One is the habitat, where you find these particular snails, and the second is the colour of the snail. So the habitat where you find the snail is the treatment. It's the thing that you're expecting to have an effect. So it's the independent variable, and the dependent variable is the colour. So the colour patterning of the snails is changed by where they're living based on predation. So in this case, these snails are called Sepian nemoralis. They come in yellows and pink colours, and with bands on them and not bands on them. So you have yellow, pink, banded pink. You find them in the hedgerow and the coast. So you can sum up, counting how many you find in each of the different areas. You can total the number for hedgerow and the number for coast. So 55 were found in hedgerow, 50 were found in coastal. You have 27 yellow, 27 banded yellow, 27 pink, and 24 banded pink. So you can sum the columns and the rows to give the total number of each one of the different colours and the total number in each of the different habitats. A special type of table is called a 2x2 disease exposure table. So you have, are the people exposed to that particular treatment or risk, so let's say smoking or non-smoking, and do they have the disease, so yes or no. So this is lung cancer yes or lung cancer no. So you can fill in this table of yes no's, dichotomous answers, in this 2x2 table to put in the numbers A, B, C and D. Now it's really important you get these A, B, C and D's, because I'm going to use them to demonstrate how you calculate the odds ratio and the relative risk. Now you cannot do this for the bigger set of tables like this. You cannot figure out the relative risks unless you've got a 2x2 table. So the odds ratio is the diseased and exposed divided by the healthy and exposed, divided by the diseased and not exposed, divided by the healthy and not exposed. Now what you want to happen is, if you've been exposed and if you've got the disease, you want A to be a big number. If you've been exposed and you don't have the disease, you want that to be a small number. So it means it's a strong causation. It's definitely causing something to happen. Whereas if you've not been exposed, you really don't want anyone to have the disease. So you want C to be small. And if you've not been exposed, you don't want them to have the disease. So you want D to be big. So A and D need to be big, B and C need to be small. So when you convert all that formula, you've got AD divided by BC. So that will be a very large number if A and D are big and B and C are small numbers. So you've got a big number divided by a small number, which will give you a big number. Now an alternative to that is another measure called the relative risk. So that's the diseased and exposed divided by the no diseased and exposed. Then it's divided by the diseased and not exposed divided by the no disease and not exposed. And equals A over A plus B over C plus D. Which, if you rearrange the formula, is A times C plus D over A plus B times C. Both of these are used when you're doing epidemiology to tell you the difference in effect between the treated and the untreated group. So between those exposed to smoking for lung cancer, for example, and those who are non-smokers. Now, graphically, you display categorical data using bar charts. Now, this is an example of a bar chart gone wrong. So what I've done is collected the number of people who are born within my class by each one of the different months. So here I can see peaks in March, I can see peaks in June, I can see lesser numbers in September and October. I've got this data, and then I can go along and I can construct an explanation. I can create a story and a narrative that fits that plot. I can look back for 9 months before March and say, oh, well, that's summer holidays. I can look at 9 months before June and say, oh, that's the beginning of autumn, let's say. Then I can look at September and October and say, well, those are the 9 months after it being really cold in January and February when it's dark and miserable. And I can make all sorts of explanations as to why the birth rates are up and down in a particular month. But all of them would be complete and utter nonsense, because the thing that's happened here is I've truncated the y-axis. It goes from 10 to 13. This is what the data actually looks like if I put the 0 on it. It's flat, it's pretty much uniform, and there's a very, very tiny bit of variation, which just happens based on pure chance. So when you're looking at bar charts, it's really important that you don't mislead by the choice of your axis on your bar charts. But it can be very easy to do if you've got a very large difference between your different groups. It can be very tempting to truncate, but bar charts, when truncated, are extremely misleading. Another kind of bar chart is called a stacked bar chart, and that gives you a total. When you've got anything that adds up to a total, such as a total of percentages, then it makes sense to use this stacked formula. So here is my time allocation for the years 2013 and 2014, divided into leave, other activity, research, supportive teaching, or teaching. Because you know my time has to be split into 100%, then you know that you're going to get a completed bar chart each time. Now, if you've got data like the two-way table, so if you have the coastal and hedgerow version of the snails, the way you would normally display data where you've got two variables that are important is what's called a nested bar chart. So in this case, you're expecting that gender, whether the baby that is born is either male or female, does it affect the way that they are delivered between standard vaginal, assisted vaginal, elective caesarean, emergency caesarean, and emergency caesarean when not in labour. Is there any effect dependent on the gender of the child? In this case, perhaps there's something that more girls are delivered normally and more boys are emergency caesareans, but it's probably not a very strong evidence in this case. The others are pretty much about the same. And elective caesarean, you'd expect there to be no gender discrimination, because that's purely dependent on the parent's choice, and it's not going to be dependent on the gender of the child in any form. So nested bar charts allow you to compare the results between the treated and the untreated group for a variety of categorical data.